And I'm sorry, my computer keeps switching back and forth between capital I and lowercase I, but anytime you see either one, it means current. This is an example of how to balance the gravitational force down on a wire with a magnetic force on the wire due to the current that the wire is carrying. We've got a wire with a mass per unit length of 0.500 grams per centimeter, and it's carrying a current of 2 amps in a direction directly south. So we want to figure out what is the magnitude and direction of the minimum magnetic field needed to lift up this wire and cancel gravity. So first we'll write down using the symbols that we use in the relevant equations. Mass per unit length is 0.500 grams per centimeter. Current is 2.00 amps, and we're trying to find the minimum B to lift the wire. The equation we will use is F equals BIL sine theta, or force equals magnetic field times current times L times the sine of theta. So what we need is for the gravitational force on the wire, given by mg, to be equal to the magnetic force given by F equals BIL sine theta. So let's write that equation down. Okay, now let's look at the different terms in this equation. B is what we're looking for. Current is given, I. The L, let's hold off for a moment to talk about that one. So first, the sine theta. Okay, well, we're looking for the minimum magnetic field. And we get to control, in this case, both the direction and the magnitude of the magnetic field. So if we want the minimum magnetic field, we would want to pick a direction so that the sine theta term would be maximum. So let's assume that we're going to pick a direction of the magnetic field where the angle between the magnetic field and the current is 90 degrees, and sine of 90 degrees is 1. So we get to eliminate the sine of 90 degree term, say that that is equal to 1. But you may be thinking, well, we don't know either the length of the wire or the mass of the wire. We're looking for B. We know the current and we know gravity, but we don't know the length or the mass. But we know the mass per unit length. So if I divide both sides, actually we're trying to solve for magnetic field B anyway, so let's go ahead and divide both sides of that equation by I times L. Now that is also equal, if we regroup terms, we can write it this way. So you can see that if we regroup terms that way, we've got mass per unit length times gravity over current. But mass per unit length, we know that. It was given in the problem. So now we're ready to plug in numbers. Before we do that, we need to make sure that all of the numbers we have are in SI units of kilograms, meters, and seconds, things like that. So current 2 amps, yeah, amp is the SI unit of current, so that one's okay. Mass per unit length, 0.500 grams per centimeter. Grams needs to be converted to kilograms, and centimeters needs to be converted to meters. So let's do that. Let's say, okay, we've got 0.500 grams per centimeter, and that's equal to, so to convert grams to kilograms, we need to multiply by 10 to the minus 3. So that's going to be 5.00 times 10 to the minus 4 kilograms per centimeter. And if we then change to centimeters to meters in the denominator, I need to multiply the denominator by 10 to the minus 2. So that's 10 to the minus 2 meters in the denominator. So the 10 to the minus 4, 10 to the minus 2, 10 to the minus 2 cancels 2 of the 10 to the minus 4. So that's going to leave us with 5.00 times 10 to the minus 2, and that is kilograms per meter. So once we have the m over L in terms of kilograms per meter, we can plug everything into the equation and solve for B. So we have E equals 0.500 times 10 to the minus 2 times 9.8 meters per second squared, all divided by I, which is 2.00 amps. Now, I didn't write down all of the units in that equation because they don't obviously cancel. The important thing is to make sure that when you plug in your numbers, you've converted everything to normal SI units like kilograms, meters, and seconds, and amps instead of milliamps, things like that. Well, we've done that. So if we do that, if we plug all SI units into the equation to begin with, then we get SI units out, and the SI unit for magnetic field is the Tesla. You plug all of that into your calculator, and you get that it is 0.245 Tesla. Now, magnetic field's a vector, so we need to find both the magnitude and the direction. Let's use the right-hand rule to find the direction. All right, so let's draw our little compass. We've got north, south, east, west, and we're told that the current is going south, so we draw the current that way. Right, we want the force to be up, an upward force. In the perspective that we're drawing this, an upward force would be out of your screen. So we want to cancel gravity, so we want force up. So normally with the right-hand rule, you point your fingers in the direction of the current, and you curl them or point your palm in the direction of the magnetic field, and then your thumb points in the direction of the force. Well, this time we know the current and the force. So what you do is you point your hand, your fingers, in the direction of the current, which is south or down on your screen. Then you point your thumb in the direction that you want the force to go, which is up, and your palm or your fingers would curl in the direction of the magnetic field, and that would be east. So the answer is B equals 0.25 Tesla to the east.